So in this problem, we're trying to find the force that is needed to support a vertical plate on which I have a nozzle that is splashing some water across this plate. So we're given the horizontal water jet that is of area AJ, average velocity VJ, and momentum flux correction factor beta J. It impinges normal to a stationary vertical flat plate, and we just want to find the required force to keep the plate from moving because of the water that is hitting it. From the given, I remind you, we have the average velocity Vj. This is the velocity that is coming out of the nozzle, and you can see that the direction is drawn to be horizontal along the x direction. The momentum flux correction factor beta j, we need this when we are going to plug in our conservation law for linear momentum. For well-defined inlets and outlets, I remind you that we have this term in which we just use the average velocity across any inlet or outlet, but because I know that my velocity is not really constant, and taking its average will make a big approximation. You can see here that across any outlet I actually have something more like this, where I have some velocity profile, and taking this average is taking the average of this profile will actually just lower the precision of my answers. So we use this correction factor beta, in which we account for the non-uniformity in my velocity. So trivially, to study the force, I use the momentum conservation law for a control volume because I have the forces on the left side of my equation. Now you can see how this equation, as we have discussed earlier, it's in vector form. So in order to study this equation, I will need to resolve the vectors into x and y components and study these directions separately. Now, because my force of interest is horizontal, as you can see here, it's towards the left, then it's trivial to me that I can just use the conservation law along the x direction, which is my horizontal direction in this situation. Along the x direction, I can see that my equation will simplify a lot because of quantities that do not have any horizontal components, such as gravity. It has no x component, so it will not be kept in my conservation law. For the pressure forces, if we actually look at my chosen control volume, for this study, I'm going to choose a control volume that crosses through the plate so that I can have this force F here included to be acting on my control volume. But for this chosen control volume, I can see that the water is actually splashing everywhere while being in contact with the atmosphere. So the pressure forces will all just contain the atmospheric pressure, and thus they will all cancel out. So I have P atmosphere everywhere here, and there will not be any net force due to the pressure. For the viscous forces, I can see that for my chosen control volume, I don't really have any boundaries at my control volume. I did choose the control volume on purpose to cross through the plate so that I can have this external force F included in my equation. So there are no boundaries or no plates in contact with the control volume from the outside, and thus there will be no viscous forces because I have no plates at the edges of my control volume or at the outer surfaces. For the other forces, yes, I do have this external force which I need to support my plate, and this force is to the left, which means it's along the negative x direction, so I'll have minus F here. And you can see how the left side of my conservation law will simplify to minus F only. Now on the right hand side, I can clearly see how this goes to 0 because I have a steady flow, and then what remains is these two components here. Now let's look at these two components, which are just the flow rate of my momentum through the outlets and the inlets that I have. So in my control volume, I have one inlet, which is right here, and this inlet essentially feels the velocity that I have coming out of my nozzle. So I can write for my inlet that I have, it's just one inlet, so I can just take the sum away and just keep beta m dot and v. Now I'm projecting along the horizontal direction, and I have vj here along the horizontal direction and beta j. So this is across my inlet. I still have my minus sign. Let's look at our outlets. Here I have several outlets. Actually, the water is splashing in all directions across the plate. Here I can see a side view, but if I look at a front view in which I have the z and y directions, my plate actually will look like this. This is my plate, and my water, which is going through this inlet, is going and splashing in all directions across the plate. So it's basically radially outwards. However, all of the outlets are in the ZY plane, which is the vertical plane containing the plate, and none of these outlets have any X components. So actually, my outlets will just cancel out because they have no X components. The outlets are in the plane of the vertical plate. So I'm stuck with just this inlet and this force F here, and thus my equation will just simplify to this. Now, m dot, which is basically the mass flow rate, I can write it in terms of the volume flow rate, and my volume flow rate can be written in terms of the area and the velocity. These are Hj and Vj. So now I got F to be equal to beta j rho Hj and Vj squared. I have some values here which I can plug in from my given. I'm not given beta j. I know that my fluid is water, so I can just use the density of water. The area of my inlet is 6 centimeters squared, which I can write over here as 6 times 10 power minus 4. And Vj is 5 meters per second. So I got this expression for my force. Now the question asks me to compare the impact of beta j. Beta j is the linear momentum correction factor, and we have studied in a previous video that we have several values for this beta j. Namely, if we have a uniform flow in which the velocity is the same everywhere, I will obtain beta j to be just equal to 1. Here I don't have to worry about the correction factor because there is no average value, it will be just the speed itself. Now, if we plug beta for this situation, I will obtain a force that is equal to 15 newtons. However, if I have a non-uniform flow, I have two special cases that I can address. I have the fully developed laminar flow. In that situation, beta j is just equal to 4/3, as we have verified in another video. And if you plug this value of beta j, you're going to obtain a force that is equal to 20 newtons. And my final special case is the fully developed turbulent flow. In that situation, beta j, we said it ranges between 1.01 to 1.03 according to the Reynolds number that we have, which determines how much turbulence we have in our flow. I'm just going to take the average value, which was 1.02, and plug it in my force, and I will obtain 15.3 newtons for this situation.